Hey everyone, today I wanted to talk about I2C protocols and how the flipper 0 can communicate with an I2C device. We'll talk about the pins that we need to connect between our I2C device and the flipper, and then we'll also talk about the wire protocol of how the flipper is communicating between the device and the sensor. So I2C is used by a lot of different types of sensors. There's EEPROMs, light sensors, gas sensors, temperature probes, and lots of other technologies that's using I2C to communicate between the sensor and the flipper. In a future video, we can look at the data sheet for one of those sensors and then also look at the code inside the flipper to implement that data sheet communications. All right, let's get started. I2C sensors use 4 wires. Pin 9 of flipper 0 provides 3.3 volts, which connects to VCC on the sensor. If the datasheet for your sensor says you need 5 volts, then connect it to pin 1 of the flipper 0. Pin 15 on the flipper 0, labeled C1, is the SDA, which stands for serial data line, and it goes to SDA on the sensor. Pin 16 on flipper 0, C0, is the SCL, or serial clock, and it goes to SCL on the sensor. Pin 18 on the flipper 0, GND, is the ground, or you can use one of the other grounds on the flipper, and that goes to the ground on the sensor. SDA and SCL pins should be connected to VCC by a pull-up resistor, and some sensors have this pull-up resistor built in, and others expect you to provide the resistor. Typically about 4.7K is the right resistance. Multiple sensors can be connected to those 4 pins, and if the sensors have different addresses. In that case, you should only use one set of pull-up resistors, and typically the devices have 7-bit addresses, so there's over 100 unique values. However, often the sensor only lets you pick between a limited set of those, either by adding a jumper wire or cutting a trace. The flipper 0 is considered the controller, while the devices are considered targets. This means that the serial clock, SCL, is only changed by the flipper 0. The serial data line, SDA, is pulled to ground by both the flipper 0 and the sensors. And this is what allows for two-way communications. Okay, let's take a look at actual data going between those wires. So our SDA wire is shown at this line. So you can see this is when it's high and this is when it's low. And then our SCL wire is here, and you can see it's high, and then you can see it's low. So we started off with our SDA transitioning from a high to a low while our clock was still in the high. That's our start. We ended our message over here where our clock went high, and then meanwhile, while it was high, our SDA transitioned from low to high. So that's our stop. So in between our start and our stop, we have our data. And so every time the clock transitioned to high until it transitions back to low for that data, our data should be at a constant value. So this is at a 0. This one was at a 1, at a 0, 0, 0, 1, 1, 0, 0, 0. Okay, so you can see that this is the 0, 1, 0, 0, 0, 1, 1, 0. And then this acknowledge was the device pulled the line low. And so that's how we got that acknowledge. And then 0, 0, 0, 0, 0, 0, 0, 1. And then this acknowledge, again, the device pulled this line low. Okay, so after our start bit, the next 7 bits are the address. And so this is the device that we're talking to. So we're talking to device with the address 23 hex. And then after that device, we either send a 0 for if we want to do a write, or a 1 if we want to do a read. And then after that, to acknowledge it, the device with this address will pull SDA low. So the flipper's been sending these bits by pulling SDA low or letting it float high. But when we do this final read or write, then after that, the device itself, if it's present, will pull it low. After they acknowledge from the device, then the flipper is going to, because this was a write, the flipper is going to send out 8 bits of data. So here's the 8 bits of data that it's writing. And then the device is going to send this acknowledge. So the device pulled this low to acknowledge it. And then after that, the flipper let the clock go high, and then the flipper kept SDA low, and then the flipper released it, and that marks the end of our message. Okay, here's an example where we're doing a read. So we have that SDA dropping down at the beginning, that's our start. And then we have our address, which is the 7 bits. That's being set by the flipper. And then we have, instead of a low before, which was a writing, we have a high, which is for reading. And then that acknowledge came from the sensor. So the sensor at address 23 pulled this line low. Did it acknowledge? And then the sensor pulled the line low, 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 and then high, low, low. So that's how it sent a 4. And then the flipper pulled the line low here for the acknowledge. And then the sensor did high, high, low, high, low, high, high, low. And then the flipper did not acknowledge that. It did a knack and kept it high. And then at the end, we had our clock go up, and then our SDA got released by the flipper and went high, and that's our stop. So in this particular case, this ACK came from the device, this ACK came from the flipper, and then this knack came from the flipper. And it just turns out that for this sensor, the protocol actually is to knack the last byte of data. So hopefully this makes sense and you understand a little more about the protocol and how it uses the SDA and SCL lines to do a start, to do its data, to do its stop, how to do read and write with reading being 1 and writing being a 0, how the ACKs happen by pulling down from either the sensor or being pulled down by the flipper. If you have any questions, please leave them below.